This video is the first of a mini-series in Module 5 about solving recurrence relations. The purpose of this video is to define what we mean by solving a recurrence relation and to outline a method to check a solution to a recurrence relation. Remember that a recurrence relation for a sequence or some other recursively defined object is an equation that relates one term in the sequence to one or more previously computed terms, along with maybe some additional computations to do. For example, we saw a recurrence relation for the triangular numbers arising from this visual pattern, and that recurrence relation was Tn equals Tn-1 plus n. That's a relation that describes how these sequence elements recur. Recurrence relations also have initial conditions that allow us to actually compute elements of the sequence by breaking terms down further and further using the recurrence relation until we're left with just initial conditions. So recurrence relations with initial conditions allow us to compute things recursively, but just because we can compute something recursively doesn't mean we should. For example, the binomial coefficient obeys a recurrence relation and has initial conditions, but computing, say, 26 choose 10 recursively would be a tremendous amount of work, even for a computer, because of the memory requirements. So instead, while recurrence relations are extremely valuable and will be kept around for all kinds of reasons, we would like instead to find a closed formula for the sequence, like we did for the binomial coefficient and the triangular numbers. The process of converting a recurrence relation with initial conditions into a closed formula that produces the same outputs is called solving the recurrence relation, and the closed formula itself is called a solution to the recurrence relation. Over the next few videos, we're going to be looking at techniques for solving recurrence relations. It can be a tricky undertaking. Sometimes a recurrence relation involves using visual reasoning like we did with the triangular numbers. And sometimes it involves fairly complex counting arguments. And sometimes it just involves guess and check. We're going to defer the process of finding solutions to recurrence relations for now, however, and focus instead on a simpler question. Given a closed formula that I think might solve a recurrence relation, how can I check to see if it really is a solution or not? For example, look at this recurrence relation for a sequence called AN. It's defined recursively with a recurrence relation AN equals 3AN minus 1 minus 2AN minus 2, with initial conditions A0 equals 2 and A1 equals 5. Now, with that information, you can check, and should check if you want some practice, that the first 6 terms of the sequence are 2, 5, 11, 23, 47, and 95. If there were a solution to this recurrence relation, it would need to produce every single one of the infinitely many terms of the sequence correctly. And it's definitely not obvious what a closed formula for this sequence might be, or even if there is one. But it's very easy to find some examples of formulas that are not solutions. A function would fail to be a solution if not all of the terms of the output happen in the same way that the recurrence relation would do it. For example, the function f of n equals 3 to the nth power is not a solution to this recurrence relation, because if we start the inputs at 0, like the recurrence relation does, it's pretty clear that the function and the sequence are not going to agree. Similarly, g of n equals 2 to the nth is also not a solution, and for the same reasons. But what about the function h of n equals 1.5 n squared plus 1.5 n plus 2? That's a closed formula, and notice that it produces the correct first 3 terms of the sequence. But then it fails at the 4th one, and so this function is not actually a solution to our recurrence relation. So that last example illustrates a very important fact. If a function produces even a single term in a sequence differently than a recurrence relation would do it, then the function is not a solution to that recurrence relation. However, if a function does produce the first few terms of a recursively defined sequence correctly, it does not mean that the function solves the recurrence relation. A finite list of examples does not show that all possible terms are generated correctly. As a more extreme example, look at this function. This produces all 6 of the correct terms that we started with. Does this make it a solution to the recurrence relation? No, because we haven't seen all possible outputs. There may be some output we haven't generated yet where the formula disagrees with the recurrence relation. And in fact, that's exactly the case. For n equal to 6, f of 6 is this number, but a sub 6 is this number. So generating examples will never prove that a function solves a recurrence relation. However, just one counterexample will prove that a function doesn't solve a recurrence relation. So if I have a function and I really think that it is a solution to a recurrence relation, perhaps because it produces the first 6 or so terms correctly, how do I prove that it really is one? I can't generate all possible outputs because there are infinitely many of them. What would a convincing general argument that doesn't rely on examples look like? Well, to answer that question, we need to change our perspective on the question, and instead of focusing on whether the function and recurrence relation produce the same outputs, let's focus on how a solution should behave. A solution to a recurrence relation would have to do two things. First, it would have to produce all the initial conditions correctly. If the recurrence relation has a single initial condition, say a0, then f of 0 would have to equal a0. If the indexing started at 1, then f of 1 has to equal a sub 1. If the recurrence relation had two initial conditions, say a0 and a1, then f of 0 would have to equal a0 and f of 1 would have to equal a1. Recurrence relations always have a finite list of initial conditions, and so it does make sense to check one by one whether the proposed solution agrees with all elements of that list. Doing so tells us that the function at least starts the sequence off the same way that the recurrence relation does. But then, once we've checked the initial conditions, a solution must satisfy the recurrence relation. This means that if we look at the equation for the recurrence relation and replaced all terms of the sequence with their corresponding function values, an replaced with f of n, an minus 1 replaced with f of n minus 1, and so on, then the resulting algebra equation must be true. The left side and the right sides must be equal. If this happens, then it means the function obeys the same recursion rules as the terms of the sequence. And if the function starts off the same way as the recurrence relation does, and then obeys the same recursion as the recurrence relation does, then this will prove that all the terms, even the ones yet to be generated, will agree. Let's look at an example with a very simple recurrence relation. This comes from the sequence 5, 8, 11, 14, 17, and so on that we saw in an earlier video. This is an arithmetic sequence, and its recursive definition would have initial condition a0 equals 5, and for n bigger than 0, an equals an minus 1 plus 3. I'd like to check that the function f of n equals 3n plus 5 is a solution. I can see that it produces some of the first few terms correctly, but remember, this doesn't imply that the function is a solution. Instead, we have two things to do. First, we need to check that f of n satisfies the initial condition. We know that a0 equals 5. Does f of 0 also equal 5? Well, a quick plug and chug shows that it does. So the initial condition is satisfied. We now need to check that f of n satisfies the recurrence relation, not by plugging in specific values of n, but using the formula itself. So here's the recurrence relation again. Separate off the left side from the right. On the left, we have a sub n. Replace this with its corresponding function value f of n. The formula for this is 3n plus 5. Now go to the right side. We have a sub n minus 1 plus 3. Replace that sequence term with its corresponding function value f of n minus 1. Remember, this notation f of n minus 1 means go to the function f, look at its formula, and replace all n's with n minus 1. This will give us 3 times the quantity n minus 1 plus 5. This simplifies to 3n minus 3 plus 5. Now let's simplify the entire expression. We have 3n minus 3 plus 5 plus 3, which boils down to 3n plus 5. Now look at the left side. This is equal to what we computed on the right side. What this tells us is that the formula f of n, first of all, produces the correct first term of the sequence, and then for every term after that, it will obey the same rules of term generation as the recurrence relation. Those two things together, a concrete function evaluation to get started, and then a more abstract argument that the function obeys the recurrence relation, put together show that all terms of the sequence will be produced correctly. Let's look at another example, going back to the earlier recurrence relation an equals 3an minus 1 minus 2an minus 2, with initial conditions a0 equals 2 and a1 equals 5. I'm going to claim that this function, f of n equals 3 times 2 to the nth power minus 1, is a solution. I'm not going to tell you how I actually got this function. That's coming in a later video. I just want to prove that it solves the recurrence relation. So let's first check to make sure the initial conditions are satisfied. There are two of them this time. When n equals 0, the sequence term is supposed to be a0 equals 2. And if I plug in n equals 0 to the formula, I get 3 times 2 to the 0 minus 1, which is 3 times 1 minus 1, which is 2. Likewise, n equals 1 should produce 5 because a1 equals 5. And if I plug in n minus 1 into my formula, I get 3 times 2 to the first minus 1, which is 3 times 6 minus 1, which is 5. So both initial conditions are satisfied. So having checked that the formula satisfies the initial conditions, we now need to check whether it satisfies the recurrence relation. So here I've copied down the recurrence relation. To check, again, I'm going to replace all elements of the sequence, which in this case are an minus 1, and an minus 2, with their corresponding function values, f of n minus 1, and f of n minus 2, respectively. So separate off the left side from the right side and work with each side independently. On the left, I have just a sub n. And like I said, replace this with f of n. F of n is the formula 3 times 2 to the nth power minus 1. Now on the right, we're going to substitute two things. For a sub n minus 1, substitute f of n minus 1. And for a sub n minus 2, substitute f of n minus 2. Now, f of n minus 1 can be written out further because this is the expression we get when we take the formula for f of n as a function and plug in n minus 1 instead of n. So that is 3 times 2 to the n minus first power, all minus 1. Likewise, f of n minus 2 is what we get when we take the formula for f of n and plug in n minus 2 instead. So that is 3 times 2 to the n minus second power, all minus 1. So here is where we are after we make all the initial substitutions. We're now going to try to simplify some more using basic algebra rules. I'm not going to do a lot of explanation of the algebra here since that is prerequisite material for this course. However, you might be rusty on some of this, and that's okay, as long as you pause the video anytime you encounter something you don't understand and take a few minutes to try to work it out yourself, and then ask questions if you need help. So in the first part, I can multiply this 3 to both terms in the parentheses. This will give me 3 times 2 to the n minus first, which is 9 times 2 to the n minus first. And then minus 3 after I multiply the 3 to the 1. In the second group, I'm going to similarly multiply the 2 through the parentheses. Now, when I multiply the 2 to the first term, I could write 6 times 2 to the n minus second power, and that wouldn't be wrong because 2 times 3 is 6. But it's simpler if I notice that when I multiply 2 to this term, there's already a 2 to the n minus second here, and multiplying that by another factor of 2 will simply raise the exponent by 1. So this is also 3 times 2 to the n minus first power. And then finally, I need to multiply this 2 to the minus 1, which is going to give me a plus 2. It's 2 because 2 times 1 is 2, and it's plus because it's actually a minus 2 times a minus 1. We can now combine the first and third terms to get 6 times 2 to the n minus first, and also the second and fourth terms to get minus 1. Now, if I peek over to the left side, these two things don't look equal yet, and we'd like them to be equal. But there's one more step I can do. This 6 here is actually the same as 3 times 2, so let me split the 6 into 3 times 2. Now this new 2 can multiply to 2 to the n minus first to give me 2 to the nth, because multiplying by another factor of 2 just raises the exponent by 1. And at last, I am left with 3 times 2 to the nth, all minus 1, and that is equal to the left side. This means that the function f of n equals 3 times 2 to the nth, all minus 1, solves the recurrence relation because it satisfies both the initial conditions and the recursion that's in the recurrence relation. So in this video, we've covered a lot of ground. We've learned about what a solution to a recurrence relation is, how to show that a function is not a solution to a recurrence relation, how not to show that a function is a recurrence relation, namely by just giving a few first terms, and then showing how to properly check that a proposed solution to a recurrence relation really is one without going through examples. Next, we need to start dealing with the question of how to actually solve recurrence relations in the first place.